Welcome back to ECE 441A 541A. Homework number 8 is due in 8 days. It's due on a Thursday, just to kind of get you thinking about the final exam, which is on a Tuesday. So we need to be keeping these 2 days in our mind, Tuesdays and Thursdays, even though we've been concentrating on Monday, Wednesday, Fridays this semester. We're now in the Bode plot section of the class, and right now, today we want to finish up sketching and system identification with Bode plots. If you want a little bit more material, you can go to the PR department, not public relations, but the prerequisite and review unit on D2L, and there's some foundational material on Bode plots there. If you want to find a little bit more or a different or an additional collection of material on Bode plots, you can find it there in the PR unit on D2L. Lab 3 is due the last day of class. Is that 2 weeks from today? Wow. Also, deliverables 2 and 3 for the project are due on that day. Deliverable 1 is due today. Final exam, as I had already mentioned, is on Tuesday, the 11th of December, and that's from 10:30 to 12:30. Here's where you can find information on analysis and design with Bode plots. In the textbook, it's chapters 8 and 10. In Sham's outline, it's chapters 15 and 16, and there's some tables that collect some typical Bode plots for transfer functions in Chapter 8, Table 8.2, and in Chapter 9, which you can now see side by side, a root locus diagram and a Bode plot, and there's additional plots there, Nyquist, etc. So you could look at those if that is of interest. Today what I want to do is quickly go through a sketch of a Bode plot, and this might be beneficial for a homework problem. Then I'll give you a quiz. Since pretty much everyone is here today, I can get a good sampling of who understands what via a quiz on stability margins and how do we find those. Then we will talk about identifying a system, a G of S, from a Bode plot. How do we extract a G of S or come up with a transfer function from frequency response information? Probably we will have to wait until after the weekend to talk about controller design, which is Unit 9 in D2L, and that we will start with phase lag controllers since we didn't focus too much on those in the previous controller design units. We'll look at phase lag. That's really more intuitive maybe from the Bode plot perspective, but when you think of phase lag, you can think about improving steady state accuracy. We usually have a couple of things that are being traded off in a control design: steady state accuracy and transient behavior. With our root locus, we were focusing mostly on transient behavior. How does our system respond to given inputs? In a phase lag design, we're more focused maybe on steady state accuracy. If I put in a step or a constant of 4, am I tracking that 4 without any error? Or what is my steady state error? And how can I improve that? Before we get into that, let's just remind ourselves how we can sketch Bode plots. Here's a transfer function, and I'm going to quickly sort of scroll through this. I think this might have been made available to you if you looked at the AC notes, the after class notes from the last lecture. Here is a transfer function, and you should start thinking about what can I focus on or what can help guide me through this process of sketching or understanding what the frequency response of this transfer function might be. What are some, well, before we get there, in the pole zero form, some of those questions are maybe easier to answer. For example, how many poles do I have? I have 2. How many finite zeros do I have? 1. Do I have, well, I'm getting ahead of myself, but do I have poles and zeros at the origin? No, there's no isolated, or I can't factor out a individual s in the numerator or denominator. Those are some ideas. And now if I have 2 poles and a 0, what's my pole 0 excess? What's this transfer function's frequency response looking like at low frequencies, at high frequencies? Those are the questions you can start thinking about, so that if you did plug this into MATLAB and MATLAB produces a frequency response plot, you can now start to question or confirm what MATLAB is giving you. Oh, I must have input the information wrong because this isn't consistent with what I thought. Those are the kinds of concepts you want to get comfortable with. But to sketch Bode plots, we typically want to put them in a time constant form, which means we want to force those constant terms in each of these factors to be 1. And that way our gain doesn't get adjusted as we're going through this sketching process. We can identify one gain factor, and then the poles and zeros can break as much as they want, and it's not going to mess up our gain calculation that we've introduced into our frequency response. To find the time constant form, I like to just factor out those constants from each of these factors. We factor out a 5 in the numerator, and that puts a 5 underneath the s, and that tells us now our time constant and our 0 location. Our 0 is located where? -5. So now we're looking on the Bode plot. When we get there, we're looking at 5, and on the phase we're looking a decade before and a decade after that, at 0.5 and at 50 for action or things happening. Correspondingly, downstairs we can factor out a 0.1. We have one pole there at a frequency of 0.1, and we have another pole at 20. And if you're thinking about this, you can say, oh, I have a pole at 0.1, a 0 at 5, and a pole at 20. That's kind of the sequence in terms of low frequency to high frequency that this behavior is happening. If we clean that up, obviously this is cooked up. I have 4 times 5, that's 20, and that cancels the 20 that I factored out down below, and I'm left with a 10th downstairs, or if I pull that upstairs, I have a gain now of 10 in my time constant form. And all of the other pieces are nicely represented in their time constant form. The time constant of the 0 is 0.2. The time constant of the poles are 10 and what? (1/20) or 0.05 seconds. So that's what you could think about in terms of poles and zeros and gain for this system. What are some key features for this particular system? And I've already sort of hinted at that, but maybe the first one that I would start thinking about is, do I have poles and zeros at the origin? Because those are always on. That will be contributing gain and phase for all frequencies. Do I have poles and zeros at the origin? Poles or zeros at the origin in this system? Hopefully you can say, no, I don't see any pole or zero. So that's one of the key features. We have no poles or zeros at the origin. And that helps us understand where the phase and the gain might begin. in our Bode plot. What's another feature that I talked about? We've identified 2 poles and 1 zero. And typically when we think about poles and zeros, one of the things that we are concerned with is how many more poles we have than zeros, because that will actually influence how this system behaves at high frequencies. What's my pole zero excess? I have 1 more pole than zero. So my pole zero excess here for this system is 1. And what can that tell me? If I now said, oh, as omega gets big, oh, and what's big here? What could you consider a big frequency or large? A decade beyond the highest break, right? So in this case, our highest break is at 20. A decade beyond that is 200. So big, in our straight line thinking, is beyond 200. So here, infinity is bigger than 200. So you don't have to go really, really big to get to omega going to infinity. But as omega is going to infinity, what do we know about the slope of our magnitude? What's it going to be doing? Can we say anything? And again, I'm putting this underneath a pole zero excess of 1. Hint, hint. So a pole zero excess of 1 basically says you have 1 pole net acting at high frequencies. And what happens to the slope for 1 pole? It's obviously sloping. I hope you believe that, because we do have a difference between the number of poles and the number of zeros. So at high frequencies we're sloping, and what's its slope? Positive or negative? The magnitude. At high frequencies, if we have a pole zero excess of 1, what direction are we sloping? Poles are downstairs, so they give us negative slope. It's a negative slope. And what magnitude is that slope? Or what's the rate of slope? How many dB per decade? We have 1 net pole essentially contributing, and a pole produces 20 dB per decade. What do we know about where our... So now we know the magnitude is going to be sloping at the very end at minus 20. What do we know about the phase of G at high frequencies? Where are we going to be at? Is it going to be sloping at high frequencies, the phase? What does phase do? And now you could simply put, if you wanted to think about this, you could sketch an S-plane and say, well, if I essentially have 1 pole over here and I'm walking up the imaginary axis, I'm looking to see how is this pole changing in terms of its angle. That angle, the biggest it can get is what? 90 degrees, and since it's downstairs, it will be a minus 90. So a single pole, the most it's going to contribute is 90 degrees, and it's negative because it's downstairs. So the phase at high frequencies, we are going to be approaching minus 90 degrees. What about the magnitude in dB? So now we kind of see what's happening at high frequencies, what MATLAB should be giving us at high frequencies. What happens at the beginning? Where is our magnitude going to start? We've already said we have no poles or zeros, so it can't be sloping at low frequencies. And what's a low frequency here? What would we consider a low frequency in this example? Or small? We want to be a decade before our first break. We don't have any action before a break, and here our first break is at 0.1. A decade before that is a tenth of that, so small is less than 0.01. What's the magnitude when j omega, or omega, is less than 0.01? That's the reason we like this time constant form. We can plug in 0 for s's, and all of those linear factors just give us a 1. And what's left over? At low frequencies, here at DC, since we have no poles and zeros, we can focus at s equals 0. We have a gain of 10, absolute gain. So what's our gain in dB? Now we plug in, getting ahead of myself, 10. Log base 10 of 10 is 1. 1 times 20 is 20. So we're starting our magnitude plot at 20 dB. What do we know now? Okay, so we know where our magnitude is starting. We know it's sloping at minus 20 dB per decade, but what happens between those two extremes? We have a pole at, what's our smallest pole? Now from top to bottom, I'm going from smallest frequency to largest frequency. The pole was at 0.1, and so it will produce a break down. Our magnitude will go down. The 0 was at 5, and that will cause our slope to change in the positive direction. And we had our last pole at 20, and that will change our slope down. So we're flat, then we go down at minus 20 dB per decade at 0.1, then we're flat after 5, and when we hit 20, we're sloping again down at minus 20 dB per decade. That's what we can expect or anticipate from this plot. And if you remember, I told you could maybe just put this chart. I went ahead and sketched this chart. If you don't have the ability to go to the bookstore and find a 5-cycle or a 4-cycle semi-log paper, you may be forced to sketch these on rectangular gridded paper. So now you have to basically create your own semi-log paper, and that's what this chart helps you do. If you look at this, you say, oh, a frequency of 1 in log base 10 gives me 0. At a frequency of 2, what's the log of 2? It's right at one of those intersecting grid lines, and you can read over and you can see, oh, that's actually 0.3. So that tells us we're 30% of the distance between 1 and 10. This plot is just showing you what happens to log base 10 between 1 and 10, and you can now use that at any decade you want. You just change it to 100 to 1,000. You know you're 30% of the way between 100 and 1,000. If you're at 3, that one's not quite so clean, but that's maybe about 0.48. Well, for our sketching purposes, we could say that's halfway between the two decade frequencies. What about 4? Well, here that's 0.6. That's a pretty nice one. 5, wow, that's pretty nice too, 0.7. And then 8, So it doesn't take you too long to figure out how to sort of go between decades if you need to look between decades and say, oh, I need to find where 3 is located between 1 and 10 on my rectangular gridded paper on a semi-log plot. Is that sort of clear? So let's now do that. I've cheated. I went ahead and created my own semi-log paper beforehand, but you can follow along. Maybe just watch and you can fill this in later. But now in terms of sketching this, we have to remember, what did we say was a small frequency and what was a big frequency? We said 0.01 or 10 to the minus 2 was small, and 200, or go up a decade, 1,000 was big. That gives us the number of cycles we might be interested in this sketch. This is the magnitude plot of our transfer function, and where did we say we were starting? What magnitude? (20 dB), and we're flat because there's no polar zero at the origin. So now we simply whistle along and we say, oh, we're flat, and you might use a straight edge. I don't have that luxury here, so that looks kind of wavy, but it's supposed to be a flat line at 20 dB until our first break, which we've identified. That's why it's helpful to maybe have these little codes on your paper somewhere. Now at omega equal to 0.1, we know our magnitude slopes down or breaks, and we change 20 dB per decade. So if nothing else happened, I would just keep sloping like that. But I now know that my next change in slope occurs because of a 0 at 5. So when I hit 5, I'm actually going to need to go flat, because I was going down at minus 20 dB per decade. The 0 gives me plus 20 dB per decade. I'm now flat until I reach my next break, and then my slope changes again. So now I can make this solid, and if I was clean, I could erase that, but I don't even know if I want to try to erase. Well, I guess we'll try. Okay. Then what do I do? At 20, I'm sloping down, and depending on where I'm at, here I'm on a grid line, but how far do I go and where do I go? Well, now I'm going to be going down at 20 dB per decade, so I might go over here and say, well, let me find 200, and now go down 20 dB from here. I think that was my... And now I simply connect the dots, and I don't have to worry about anything else. I can just draw my straight edge all the way until is the biggest frequency that I want. Is that clear how that sketch was created or produced? Pretty quickly. You could do it quicker if you weren't having to talk through it like I'm doing now. What about the phase curve? Where do we begin? Did we have a polar 0 at the origin? No. So what's the angle at low frequencies? What's the angle of 10? We have a real number that's 10. You could plot that 10 on a complex plane and say, oh, that's on the positive real line. From the origin, what's the angle from the origin to that positive 10 number? 0. So the angle is 0 at low frequencies. And then what happens? When do I have to worry about? Now what I've said is I have an angle of 0 degrees until when? My phase is what? In these straight line approximations, it's distributed across 2 decades, and those 2 decades are centered around the break frequency. So centered around 0.1, I have a slope that goes from 0 to minus 90 due to the pole, and a decade before 0.1 is 10 to the minus 2 or 0.01. I'm going to begin sloping here, and I would go all the way down to minus 90 at 1, a decade beyond 0.1, and that would be my contribution of phase due to that one pole at 0.1. But do you see what's actually happening now? The 0 at 5 actually backs into, or its contribution will influence what's happening less than 1, because the 0's phase starts at 0.5 and ends at 50. So now if I wanted to think about that one, I would say, oh, here's 0.5, and there's 50, and what was my other one? 20, so let me go ahead and sketch that. And these are then flat from all of those points onward. So if you sketch all of these starts and stops of your phase, you can now connect all of those different slopes. I'm only sloping due to the one pole until I reach 0.5, which is 70% of the distance between 0.1 and 1. Then what happens? Now I have something sloping down and something sloping up with the same slope. They cancel, so I'm flat until what? Until I hit 20, or 2, and that's when my phase of my pole kicks in. And what happens now? Actually, wake me up. What happened when I hit 1? When I hit 1, I now have to go up, don't I? Because my pole quit contributing a negative slope. So now at 1, I have to go up at 45 degrees per decade until I hit 2. And then what happens? Now I'm flat until, if I had done this right, until I hit 50, and then I go down, because where did I say I needed to end up in terms of my phase? Minus 90. For high frequencies, I need to be at minus 90 degrees. And now you can see that these poles and zeros, their phases, all sort of sing together or play together in an interesting way, but you kind of then transition from 0 to minus 90 over this range of frequencies from 0.01 up to 200. There's the phase plot. We clear on that? Let's now do the quiz. And here I want you to think about stability margins. How do I determine how stable this system is, or is it even stable? How do I go about that? How do I infer stability or stability margins from frequency response plots? And this will be on the final. This will be a easy question on the final. How do I find the stability margins? What are those? What am I talking? Do you remember the two words that you have to remember when you're talking stability margins? What do you sketch in a Bode plot? Two plots, one is magnitude and the other is phase. So now we have a gain margin, that's due to the magnitude, and we have a phase margin. And those are all based on what's the magic point for stability. We had this, which in a frequency response becomes that. So now we're interested in when g of j omega is close to -1. What frequencies put me close to -1, which is one at -180. So those are my two values. I want to find a magnitude of 1 and I need to find a magnitude of -180 and use those to help guide me to determine these stability margins. Where do I find a magnitude of 1? At 0 dB, and so now I'm looking to try to find at what frequency am I actually equal to 0 dB. So what's the gain crossover frequency? Omega sub g. Can you read that? It's 30% of the distance between 1 and 10. If you can see the grid lines, it's about 2. So I'm just going to say that the gain crossover frequency is 2 radians per second. Everybody clear on where that came from? What's my phase crossover frequency? And what do I mean by that? Now I'm looking for where does my phase curve cross -180 degrees. So I simply look at -180 and I come over here and I say, oh, that's occurring about right there. There's my phase crossover frequency, and that's a little less than what? 30. So we could say that's maybe, I mean, you could eyeball this, and it's subjective. So on the final exam, don't expect, well, maybe I will make it an exact, no. So if you get close, you'll probably get credit. So 4 digits, significant digits of accuracy is probably close enough. No, it's going to be eyeball. So now what do I do with these? So now you've gotten maybe 30% of the credit on the final by identifying omega sub g and omega sub p. Just for this problem, not for the whole final. Darn. Well, maybe for you guys coming here on today, maybe you will get them. Anyway, now what do we do? How do we use omega sub g and omega sub p to find stability margins? Now we simply translate these two frequencies, wow, to the other curves. So in this case, we want omega sub g tells us what? That we have a magnitude of 1. We want to know how far away are we from -180 when we have a magnitude of 1. So if we come down here, we see, oh, here is our distance from the blue curve, our Bode plot, to -180. This is actually going to be our phase margin. We're not below -180, so we are stable based on this margin. And we can now say, oh, well, it's a little bit less than -90 and not quite all the way to -135. So it's somewhere between a phase margin of 45 and 90 degrees. And you could then eyeball that and say, well, let's say that our phase margin is 75 degrees. Our gain margin is determined in a similar way. Now we say, well, we're here and we are at minus 180. We want to know how much gain can we increase before we reach a value of 1, or on this dB plot, a value of 0 dB. So here is our gain margin. And that's what, about 30% of the distance, or 60% of the distance between 0 and 50. So we could say that's about 30 dB, or let's just get really precise, 28 dB. Are we okay with where those numbers are coming from? Can you do this on the final exam? Identify the gain crossover frequency, the phase crossover frequency, and then determine how much I can adjust the phase to give me my phase margin, and how much can I adjust the gain to give me my gain margin. That's stability margins. And this particular system is pretty stable. You could crank up the gain 28 dB before you become unstable, or you could change the phase by 75 degrees, and the phase a lot of times is associated with delay in your system, so you can tolerate a little bit of delay in this particular system. Let's now look at another topic, which is finding G of S from a frequency response. This is now system identification. Can you tell me anything about this transfer function, G of S, by looking at its frequency response? What can you tell me about this system just by quickly kind of looking, eyeballing this Bode plot? Can you tell me anything about poles and zeros in terms of their existence, where they're located? Can you tell me any of that information from this plot, just big picture wise? So it's ending up at minus 270, isn't it? So at high frequencies, what do we know? We have 3 more poles than we have zeros. We don't know that we have 3 poles. We right now can only say we have 3 more poles than zeros. The pole zero excess is 3. Is that okay? We may find that we know more than that, but from right now, just looking at, from G of j omega, that's going to minus 270 degrees for large omega, and that says that our pole zero excess is 3. What do we know at low frequencies? Can we see where our phase is beginning? It's at minus 90. What's that say? At low frequencies, we have a minus 90 degree angle for G of S. What does that tell us? Did we have a minus 90 degree angle here? And what did we have here? Wow. We had no polar zero at the origin. So if we're starting with some angle at low frequencies, we must have a polar zero at the origin, or poles or zeros at the origin. What's minus 90 correspond to? Negative angles are associated with poles, so that's telling us we have actually a pole at the origin. So what do we know? Now we know that G of S is some k. We have a pole at the origin, and now we have some factors. we need 3 more poles than 0. So here I've just arbitrarily put some factors in there. Can we identify where these factors are? So here I'm saying, can we come up with the poles underneath these S's in this time constant form, and can we find the K from this Bode plot? I don't know. How do we do that? How can we infer information from this? If the poles and zeros were well separated, let's say separated a decade apart, it might be pretty easy or easier to start seeing slope changes in the magnitude and transitions in the phase. But here, maybe it's kind of mixed up. That phase curve looks pretty smooth. But can we tell anything from where the phase curve starts and where it finishes? And if that's the case, can we infer anything about poles and zeros from that information? If that's confusing, let's go back, and here is a g of s. I did this right before class. That's 1 over s plus 1. We are doing straight line approximations, which is an approximation. And this is the actual curve for a single pole factor. And what's happening a decade before 1 in the phase? Where's our angle? Is it at 0? No, because we have been approximating it that way, but it's actually down, let's say, minus 6 degrees. It's actually minus 5.7 degrees for a single factor. But we're just making the approximation of a straight line connection from 0 down to minus 90, and you can see that we're 6 degrees off at the ends. What I'm trying to indicate by that is, if we now go back, can we sort of say, oh, what frequency are we at minus 96? Because we're starting at minus 90. Where are we at minus 96? That might give us a clue as to our pole's break frequency. Is that clear? And just eyeballing this, that looks like it's at about 1. So what's that tell us about our pole? And now we have to remember that these darn phases spread their contribution around the break frequency. And they spread it a decade before and a decade after. So this break is starting to influence us at 1, which means that it's really breaking where? A decade higher than that, it's breaking at 10. So we are actually seeing now a pole that looks like it has a break at 10 radians per second. Now, do you see this phase or magnitude plot going flat or changing slope in a positive way? Anywhere, the magnitude. No, it looks like it's just gradually going down. I don't see that there's any positive or flatness to that, so there's probably no zero factor, is what we're trying to conclude from that. Okay, now I need 3 poles more than I have zeros, and if I don't have a zero factor, I'm thinking maybe I just have 3 poles. And I had 1 at the origin, I've got 1 at 10, where's my third pole? Now let's slide all the way up to high frequencies and say, where am I minus 6 or 6 degrees before minus 270? And maybe that will give me my break frequency at the highest pole. So if I come back here and say, well, that looks like it's at about in there somewhere. Now you could look at those tick marks and say, well, that's maybe about 800. Well, a decade before that is where the pole was breaking. So now we have concluded that maybe that's what we have for our factors. We have a pole at the origin, and we have two other poles, one at 10 and one at 80. So we've essentially said that these aren't going to be there. How do we find K? How are we going to determine K? What happens at low frequencies? Well, that darn pole at the origin is going to be present, isn't it? It's always contributing some information to the magnitude. But those other two pieces, if S is small, the pole factor at 10 and the pole factor at 80, we can kind of neglect. If S is small, those are going to be looking like 1s. So at low frequencies, this G of S looks like K over S. Is that okay? So for low omega, G of S is approximately K over S. If that's the case, can I now look at G in dB and get a number? Well, if I go back here and I say, oh, I didn't have any breaks until 1 is what I was thinking, well then actually I don't have a break until 10, do I? So at omega equal to 1 or before 10, all I have is K over S active. So K over S is active all the way up to here. Yay! So that means that I can actually look at where this magnitude plot before that goes through 0 dB, because I know my magnitude at 0 dB. The magnitude of my K over S is what? At 0 dB. When it's 0 dB, it's 1. So now, when this is, and the reason I'm able to do this is because nothing is happening break-wise before that crossover frequency. If I had a crossover frequency before, maybe I go back here and focus on what that expression is doing dB-wise and frequency-wise. What I'm wanting to do now is try to find the frequency where that happens. And if you can see that, that's actually at an omega equal to 2. Because it's a little bit beyond 1, it's at the tick mark, I'm hitting 0 dB. So what I'm trying to say is G, the magnitude of G in dB is 0 at omega equal 2. Or that now says that this magnitude of this magnitude of K, J omega, when omega is equal to 2, in absolute terms, is equal to 1. So that now I can say, oh, the magnitude of K over omega, since the magnitude of J is 1, I now know that this is equal to 1 when omega is equal to 2. Or I can now say that K over 2 is equal to 1. K is now equal to 2. Now I've identified my transfer function from the Bode plot. I now can say that G of S is a K, which was 2, S over 10 plus 1, S over 80 plus 1, and that's now inferred from this frequency response information. I have a third order system, a pole at the origin, a DC, no, not a DC gain. What's my DC gain? What's the gain of G of S at low frequencies? We could go on and on. Where's DC on this plot? It's not there, is it? We'd have to keep marching, marching, marching to the left. We'll never hit DC on a semi-log plot. Our magnitude is just going to go up, up, up. We have an infinite magnitude at DC, and that's good in terms of steady state accuracy. Because that says, oh, we're going to be completely locked on to a constant if we can stabilize this system in the closed loop. We will pick up with that. Maybe I'll give you another system ID with after-class notes. Maybe not. Who knows? But we'll pick up with Bode plot design the next time we're together. Enjoy your break.